Probably the most interesting family or the group when it comes to chemical reactions in our syllabus is P block elements, simply because it is the biggest. We have talked about one portion of P block, that is boron and carbon family in standard 11, and nitrogen, oxygen, halogens and noble gases. These are the four families which we are going to talk about in this segment. Let's begin. This is our discussion of NCERT questions. They are very important, and especially with respect to inorganic chemistry, you would find that these questions of NCERT are valuable in competitive exams as well. So pay very special attention and let's begin. Discuss the general characteristics of group 15 elements with reference to their electronic configuration, oxidation state, atomic size, ionization enthalpy and electronegativity. So 5 typical trends have been asked. What do? Let's begin. Electronic configuration. Typically in group 15, if you talk about electronic configuration is NS2 NP3. Please note 3 plus 2 is 5. 3 plus 2 is 5. And when we talk about group 15, group number minus 10 is equal to number of electrons in S plus P shells. This is a phenomena for P block. Please note this is not true for every family. This is only for P block. So electronic configuration is NS2 NP3, and if you make a box diagram, this is the way it looks like. Pay very special attention. It has a special characteristic, extra stability of half-filled p orbitals. What about oxidation states? Oxidation states are again very interesting because it has 5 valence electrons. One common oxidation state is plus 5. Okay, so you have nitrogen, phosphorus, arsenic, antimony and bismuth. Do all of them show plus 5 state? Yes, all of them do show plus 5 state, and not just this. All of them also exhibit plus 3 state. Nitrogen is very funny in the sense, nitrogen, because it is a part of organic compounds, it can exhibit all the states from minus 3 to plus 5, including even fractional states. Wow. So plus 5 and plus 3 are throughout the group. Yes. In addition, nitrogen can show very interesting multiple other oxidation states also, because when nitrogen is a part of organic compounds, there are nearly infinite number of organic compounds, and that is why any possible oxidation state is true. Please note upper limit is plus 5. Then you also have plus 3. And is there a lower limit? Yes. The lower limit is minus 3. Can all of them show minus 3? Yes, indeed. All of them do show a minus 3 oxidation state. This is the general characteristic of group 15 with respect to oxidation states. Also, please remember, the stability of highest oxidation state decreases down the group as per inert pair effect. That means that plus 5 of bismuth is most unstable, or this is least stable. And interestingly, not nitrogen, but phosphorus in plus 5 is most stable. Somehow nitrogen also has strange ideas about nitrogen being very electronegative. So nitrogen also doesn't like plus 5 state much. Nitrogen is most stable in oxidation state 0. What? Yes. Look at nitrogen around you. Which is the oxidation state? It is in air, it is in your breath. Yes, and the oxidation state of that nitrogen N2 is 0. Nitrogen is most stable in 0. That is a strange exception. Phosphorus is most stable in plus 5. And the stability of plus 5 state decreases, and bismuth is least stable in plus 5 because of inert pair effect. This, my dears, is the trend of oxidation state in group 15. What about atomic size? Very simple. On moving down the group, you keep on adding extra shells, and as you keep on adding extra shells, atomic size increases down the group. So atomic size very consistently increases down the group, it has any exception? No, it has no exception. But again, don't forget, nitrogen to phosphorus is a rapid rise. Then arsenic, antimony and bismuth. The rise is, the increase in sizes, rather there's always an increasing order because more shells are being added. But the rate of increase goes down. Why? Because between phosphorus and arsenic you have D block, and between antimony and bismuth you also have D as well as F blocks. So if extra protons are being added to the nucleus, you find increases there, but not as much, simply because the rate of increase goes down with increasing number of periods. If you're confused, I'll just tell you some more data. See, it's like whenever we are moving from N to P, one extra shell is added. But between these, if you see, the difference in atomic number is 8. This difference is 18. This is 18. And this is 32. So one extra shell and you have just 8 extra protons. So size increases. You have one extra shell, but you have 32 extra protons in the nucleus, so nuclear pull increases and the size does not increase as much if you move down the group. This, my dears, is a very detailed analysis of trend of atomic size on moving down the group. Although sometimes people would say, just this much is sufficient. If you're happy, this is one line is very good. This is a very deep concept which I have told you. So if you take that, that is icing on the cake, but at least take the cake. Don't miss this. When we talk about electronegativity, as we move down the group, size increases, yes, very much. And electronegativity also decreases. So most electronegative is N. Then phosphorus is substantially less. And then we have arsenic, antimony and bismuth. Antimony and bismuth have nearly same value of around 1.9. And nitrogen is highest with around 3. Phosphorus goes around 2.2 or something. And that these are roughly the values of electronegativity down the group in group 15. What about ionization enthalpy? As size increases, you find ionization enthalpy also decreases. So if you're talking about first IE, then nitrogen is highest, then phosphorus, then arsenic, then antimony, and then bismuth. There is a consistent decrease down the group. Reason? As size increases, ionization energy decreases. Why does the reactivity of nitrogen differ from that of phosphorus? Now this is a very interesting question. Nitrogen, because nitrogen belongs to period 2. Now second period elements are sometimes called typical elements. And why are they typical? Because they're different. And why are they different? 4 points. Number 1, small size. Second, high ionization energy. This is for nitrogen. Third point, high, relatively high electronegativity and absence of D subshells. And when we say absence, it means no 2D subshells exist. 3D is there, but then that is useless because energy is very high. So you find that nitrogen has a very small size as compared to phosphorus, and because of that very small size, there is a special property. What? Nitrogen can form p-pi bonds with other small atoms like carbon, okay, with carbon, nitrogen, boron, etc. Not many in etc. Largely with carbon and nitrogen. Because of this, now, and can phosphorus do this? Phosphorus can't do this. Even nitrogen can form a very good bond with nitrogen also, oxygen also forming. Like N triple bond N. Very, very good, very stable, one of the very strongest covalent bonds in nature. On the other hand, P triple bond, P is very stupid, unstable bond. Phosphorus, arsenic, antimony, etc. they prefer forming only single bonds. Bismuth, that's very different. It forms metallic bonds. So you find nitrogen is capable of forming double and triple bonds while phosphorus cannot, and that is the first very major difference. Reason being small size and high electronegativity of nitrogen as compared to phosphorus. That is why the first difference comes here. Also, when you talk about d subshells, nitrogen cannot expand its octet. So phosphorus can form PCl5, nitrogen cannot form NCl5. That again comes as a major difference. Not just this, when we talk about non-expansion of d subshell, which means that phosphorus can form P double bond O, RRR, something like this, trialkyl derivative of this P double bond O. Nitrogen cannot give you similar compounds. Because of this, why? This is a compound in which back bonding is being done between oxygen and empty d orbitals of phosphorus. Nitrogen cannot do this because d orbitals are missing. These, my dears, are the major reasons because of which nitrogen is a very different chemistry as compared to that of phosphorus. Discuss the trends in chemical reactivity of group 15 elements. Now, this is a very interesting, a very wide, all-encompassing question. It has many ideas, many concepts involved. So first, I'll give you some very general ideas. Number one, if you look at nitrogen N2, nitrogen exists typically as N2, and N2 contains N triple bond N. It is one of the strongest bonds in nature. Nitrogen is very, very happy and very stable as N2, and that is why dinitrogen becomes inert. Yeah, this is unreactive. Oh, has it become like a noble gas? Not really. It is of course more reactive than noble gases, but then compared to all other gases, dinitrogen has very poor reactivity. Why? Because it already is quite stable. So, elemental nature, if you see, most inert element in the whole family is nitrogen. Why? Because N triple bond N is very, very stable. Please remember, atomic nitrogen is very reactive. If you can break this triple bond and just convert it to nascent nitrogen, that would be very, very reactive, but then that is not the state in which it exists. So all you have is N2, and N2 is fairly nicely, happily inert. What about phosphorus, arsenic, antimony, and bismuth? Top to bottom, the group is not very reactive, honestly. Bismuth is also a very dull kind of a metal. I would not say it's a noble metal, but yes, it is not a very reactive metal as well. So nitrogen is a non-reactive non-metal and bismuth is a non-reactive metal. So by sandwich theorem, everything is non-reactive. There is no sandwich theorem in chemistry. Phosphorus, arsenic, and antimony are relatively more reactive as compared to top and bottom nitrogen and bismuth elements. Please note, I am not talking about compounds. I am not comparing the reactivity of their compounds. I am just talking about if we have elemental nitrogen, phosphorus, arsenic, antimony, and bismuth. You find elemental nitrogen is N2, which is least reactive. Elemental bismuth is just bismuth metal, which is also not very reactive, but at least bismuth is a little more reactive often as compared to nitrogen. Now, when you talk about phosphorus, arsenic, antimony, they are kind of golmaal. Interestingly, the question has been asked in NCERT, but the answer which they might be expecting from NCERT is not given in NCERT, which is the beauty of NCERT. They can ask you anything without telling you anything. Why? NCERT is giving answers. I'll tell you what NCERT writes. But before that, let me just answer the actual question. The question is a good one. The only problem is the answer is very vague given in the text. Now, we talked about a general trend. Reactivity with water. Can they react with water? No. Nitrogen, phosphorus, arsenic, antimony, and bismuth. Each of these 5 metals under room temperature and pressure has absolutely no reactivity with water. As a matter of fact, phosphorus is very reactive. White phosphorus can burst into flames in oxygen, in air at 35 degrees Celsius. Still, phosphorus is kept stored under water. Why? Because it does not react with water and it does not dissolve in water as well. So the full family is unreactive towards water, and they're also insoluble in water. I repeat, I'm not talking about any compound, I'm talking about elements. nitrogen element, phosphorus, P4, arsenic, antimony, bismuth, in elemental state, they are totally unreactive towards water. The second point, these 2 points are not clearly given in NCERT. Why the hell are you speaking them? Because they are the correct answers to the question which is asked. Okay. Now, about a wrong answer which is given everywhere. Why? Why are you giving a wrong answer? Because it is given in NCERT, it is given everywhere, so that you shouldn't feel that I'm escaping out something. So I'm giving you, and probably if the question is asked in board exams, they will expect you, they will expect the stupid answer from you only. So just to satisfy their expectations and so that you can get marks in board exams, I'm giving you a wrong and a misplaced answer which is mentioned in NCERT. What is that? I repeat, I'm not doing it out of happiness. It is just that you don't care for science much. You rather care for the marks. So that is, we have this unfortunate trend in our education system. So I'm telling you the wrong answer and also why it is wrong. I'll tell you both. NCERT, when it comes to chemical reactivity, mentions 4 points. 1, reactivity with hydrogen. Second, reactivity with oxygen. Third, reactivity with halogens. And fourth, reactivity with metals. Out of these, the correct answer to this question is only in 4th part, which is metals. If you are examining the reactivity of halogens, of group 15 with metals, typically they tend to form M3X, where metal is +1 and X is -3. X is not halogen. X is, this is group 15 element. Okay. So typically they form tri-positive anion. Yes, tri-negative anion. Yes, they form a tri-negative anion. Like they form nitride, phosphide, arsenide, bismuthide, antimonide, and even bismuthide. For example, if they react with alkali metals or alkaline earth metals, like you get compounds like sodium bismuthide, calcium phosphide, magnesium nitride, such things are possible. So typically they form -3 anion when they react. Honestly, this is partially correct. This is what is mentioned in NCERT, I'm telling you this, and this is what is expected for you also to write down. But the true question is the trends in reactivity. That means, can we compare how reactive is nitrogen as compared to phosphorus or arsenic or antimony or bismuth? Such data is not mentioned, and although I can tell you, but I don't think I should bother you so much. If you write this much, it is sufficient. I repeat, scientifically, this is not the answer to the question which has been asked. Anyways, why you're making so unnecessary fuss? Question is there, my answer is there. We are getting marks for this. Why should you worry? My worry is the murder of science, nothing else. And I think one should worry about this. Now, the problem is, they have also mentioned that you should discuss the trends in reactivity with hydrogen, but they have not mentioned how reactive is hydrogen towards nitrogen, phosphorus, arsenic, antimony, bismuth. The same they have not mentioned for oxygen and halogens as well. The trends they have not mentioned. They have just told you the outcome. Like with hydrogen, you get EH3. For example, nitrogen can form NH3, phosphorus can form PH3, arsenic can form ASH3, SBH3 and BiH3. They mention this, that these hydrides are possible. And then they start talking about the trends of reactivity of hydrides. I repeat, this is not the trend of reactivity of the elements. But since nothing else has been given, I'll just mention. Down the group, bond length, increases. So you find stability decreases. That means ammonia is more stable and bismuthine is least stable. So reducing power increases, and not just that, basic strength decreases. I've told you 4 properties. We can talk about more also. But again, this is what is expected for you to write down the trends. But I repeat, these are not strictly speaking trends of reactivity of elements. These are the trends of reactivity of element hydrides, which is best explained in NCERT. Nonetheless, this is as regards hydrogen. What about oxygen? With oxygen, they can form E2O3 and E2O5. Typically, all of them can do this. N2O3, N2O5, P2O3, P2O5, AS2O3, AS2O5. Typically, because they both show oxidation states of +3 as well as +5. That's it, that's it. And not just that, amongst E2O3 and E2O5, more acidic is +5 state, and +3 state is obviously relatively less acidic. But then, this is not the trend of reactivity. I know that this is not the trend, but this is the only thing which is mentioned in NCERT, and this is the only answer you're supposed to give if you want to get marks. This is a match fixed. What about X2? Model of Science continues. In X2, you have, well, you can form EX3 as well as EX5. Nitrogen will give you just NX3. Nitrogen will not give you NX5, but E can be phosphorus, arsenic, antimony. To some extent, bismuth also, but bismuth also loves forming just +3 because of inert pair effect. Nitrogen does not form +5 because there is no presence of d orbitals in nitrogen. Nitrogen cannot expand the octet. Bismuth can expand the octet, but bismuth doesn't want to expand the octet. It just stays because of inert pair effect. Bismuth just loves to stay in +3. So you have BiX3 also. Although bismuth can form BiF5, that is possible, but fluorine is more reactive, so it can form BiF5. Chlorine can form BiCl5 with great difficulty, and BiBr5 and BiI5 do not exist. So for all practical purposes, nitrogen and bismuth just go to +3, and others can go to +3 as well as +5. I repeat, these are the properties of the products. This does not explain the trend of reactivity, nor has it anyway been mentioned. This is the expected answer, although this is very different from the question which has been given. But this is a standard popular answer everywhere on earth, and this is what is expected by NCERT also. So my suggestion for NCERT people, change the question or give more data in the answer. Why does ammonia forms hydrogen bonds while phosphine does not? The reason is very simple. For hydrogen bonding, the electronegativity difference between hydrogen and the other element has to be very significant. Now, electronegativity of nitrogen is 3 and electronegativity of phosphorus is 2.2. And electronegativity of hydrogen also is around 2.2 only. So pH bond is nearly non-polar. There is no significant delta plus charge on hydrogen atom, and for hydrogen bonding, sufficient delta plus charge on hydrogen atoms is necessary. Then only they can undergo any kind of hydrogen bonding with any other species which has some delta minus charge. Phosphine has no delta plus, sufficient delta plus on phosphorus or hydrogen, or sufficient delta minus on either of them. Because of nearly non-polar nature of pH bond, phosphine is just not capable of forming any hydrogen bonds. How is nitrogen prepared in laboratory? Write the chemical reactions, chemical equations for the reactions involved. My dears, there are 3 typical methods. Wow, 3, yes, there are 3 typical methods for preparation of nitrogen. Lab methods. First one. You take ammonium nitrite NH4 NO2. So, you just take NH4 NO2 solid and warm it gently. You would get water vapors and nitrogen. That's it, very simple. And sometimes having NH4 NO2 is not very easy or simple or straightforward. Then people resort to this. You take ammonium chloride, so you have NH4 plus, and then you take NaNO2. They are easily available. You mix them thoroughly in solid state and just warm it. What do you get? NaCl, you can separate out. See, that's very simple. If you just remove NaCl, you have NH4, NO2, same. So you have NaCl plus NH4, NO2. And have you ever noticed -3 and +3 oxidation states of nitrogen? Ammonium has -3, nitrite has +3, average is 0. You heat them and you get the average, which is 0. There we are. This is the first method, gently warming NH4NO2. And now when you have this, I hope you will understand that there is nothing special about chloride and sodium here. Instead of sodium, if you have potassium or barium, it's okay. Instead of chloride, if you have sulfate or phosphate, then also it's okay. They don't make any difference. They'll just come down in the salt. Say if you have potassium and sulfate here, you will get K2SO4. The other portion of the reaction will be the same. Right? Okay. This is first method. Is there a second method? Yes. And what is that? It's a very famous method. Gently warming ammonium dichromate. It's a very beautiful volcanic reaction. Also, yeah, volcano-like looking reaction. You have ammonium dichromate. And you just heat it. Very important reaction. Many times it has been asked in competitive exams as well. And then, what do you get? Of course, you get nitrogen. You get lots and lots of water vapor. And you get green colored Cr2O3, while this is orange in color. Look at the beauty. This orangish thing turns green. It gives you out green colored ash. The classic volcano reaction. Ammonium dichromate. That, my dears, is the second method. Is there a third method? Yes. If you want ultra pure nitrogen, small quantities, then you take barium azide. Now this is very expensive, and if you gently warm barium azide, it just decomposes. It gives you barium plus nitrogen. What is this? This is barium azide. It is obtained with difficulty, but if you can afford it, you get again ultra pure nitrogen. Why small quantities? Because it is expensive. I mean, if you can afford large trucks of barium azide, heat it, you get large quantities of ultra pure nitrogen, also no problem. These are the three methods. How is ammonia manufactured industrially? Now this is a Nobel Prize winning question. Ammonia is industrially manufactured by a classic process called Haber-Bosch process. Actually, Haber got a Nobel Prize for this, and later on Bosch modified it and Bosch got another Nobel Prize for it. So, well, it's a 2 Nobel Prize worth of a process. So, let's take a look. The process appears seemingly deceptive and very simple. Nitrogen and hydrogen, if they are compressed together in the ratio 1:3, in the presence of catalyst, they can react to give you ammonia. And they release some heat also. Small quantity of heat, but they release some heat. So N2 plus 3H2 can react to give you 2 times ammonia. Yes, indeed. In the presence of a suitable catalyst at high temperature and pressure. This essentially is the so-called Haber's process. Now, in this, nitrogen is derived from distillation of air. You take air and you distill it and you separate nitrogen from that. Hydrogen comes from cracking of petroleum products. So when we take petroleum and we refine it, in that process we get a lot of hydrogen, and that hydrogen, these are the sources of N2 from air and hydrogen from petroleum refining. These are the ones which are used mostly, and then they are subject to Haber's process. What are the details of the process? This is the way. You have H2 and N2 from the respective sources, you mix them and you compress them. Now 20 megapascals. That is, now 10 is to 5 Pascal. Now, 1 megapascal is around 10 atmosphere roughly. So this is around 200 atmosphere pressure, which is high pressure. And then this ammonia is passed, high pressure ammonia is passed through and is heated also to around 700 Kelvin, which is around 400 to 500 degrees Celsius. The catalyst is potassium aluminate, K2O plus Al2O3, and iron oxide is also a part of catalyst, right? Now, they react to produce ammonia, and the product is, you have some unreacted N2 and H2 and you have some ammonia, of course. What do? You take out this and you cool it and condense it. Please note that ammonia is more polar than N2 and H2. It has a much higher boiling point. It is much more easily condensable. So people freeze it and condense it. You get liquid ammonia. Minus 33 degrees Celsius barely. Ammonia condenses. But N2 and H2 don't condense. They can be taken, the unreacted N2 and H2 taken out. They're again pumped, pressurized and mixed here. And again they're passed through catalyst. And this process keeps on repeating till you get lots and lots of ammonia, as much as you wish. And this, my dears, is the classic Haber-Bosch process for industrial manufacture of ammonia. And this brings us to the next question, which says, illustrate how copper metal can give different products on reaction with nitric acid. Now, this is very interesting and very important. How? There are two classic reactions. If you have concentrated HNO3, if you have concentrated nitric acid, if it reacts with copper, you would get a different product. And if you have dilute nitric acid, you will have a different product. Why? Concentrated nitric acid reacts with anything usually, if it reacts at all. It will react, it will oxidize the other party and it gets itself reduced. Wow. What do you get? You get copper nitrate and you get reddish brown NO2 gas, and water is of course at times just free. What? Just look at this. Copper with 4 nitric acid give you this and 2H2. I hope this is balanced. Yeah, I believe it is. What about dilute nitric acid? Just imagine that, see, in concentrated you had lots and lots of nitric acid. Now if nitric acid is dilute, that means you don't have enough nitric acid. Can you imagine what happens? Copper reacted with some tiny bit of nitric acid, fine. And even if you get NO2, now NO2 itself will get reduced. Why? Because there is more copper, and since nitric acid is less, this product NO2 can react further. And you can get copper getting oxidized to copper nitrate. NO2 gets further reduced to NO. This is reddish brown. And NO is colorless. NO is colorless. Yes, it is paramagnetic and colorless. Just balance this. And you will have nitric acid, 4H2. How many NOs? You get 6 and 2, 8, 2 NOs. Yeah. This, my dear, is what you would obtain. Fascinating, absolutely fascinating. This is what you get. These are 2 standard NCERT answers. I am telling you 2 more possible reactions. If copper reacts with moderately concentrated nitric acid, somewhere in between very dilute and very concentrated, and you cool it also, cool the products, don't make it very vigorous, you get copper nitrate, yes, you get N2O3, oh my god, and you get water. Is that a possibility? Yes. And how much would that be? Around 2 Cu gives you around 6 nitric acid. You have 2 copper nitrate, 2 N2O3 and 3H2. This is also possible, but a relatively rarer reaction. Also, there is one more. If vapors of nitric acid are passed over heated solid copper, high temperature, red hot copper, you have vapors of nitric acid passing over it, well, you get copper oxide and you get nitrogen and you get water vapor. Oh my god, this is the case. Yes, this is the case. You find +5 goes to 0, and this is 2. So this is 2 and 5. Okay, you have 5 CuO indeed, and you have 1 H2O, and how much nitrogen? 1 nitrogen. That's it. This is balanced. Perfect. So you have 4 possibilities. Nitrogen coming down to +4, +3, +2, and 0 states. There are 4 ways in which copper can react with nitric acid, out of which you're expected to write only these 2 are the major ones. If they ask you this question, just give the violet answer. But the red reactions are also possible, and sometimes they may be asked separately. Of course, not in board exam. In other exams, it is a possibility. If they are there, at least you know all the answers. Give the resonating structures of NO2 and N2O5. Oh my God. Let's take a look. NO2 goes like this. There is an unpaired electron, and this is something which we can't help. So nitrogen has an incomplete octet. Yes. You have these as formal charges. So bond order of NO bonds is 1.5, and octet of nitrogen is incomplete. Unpaired electron is present on nitrogen, and these are the contributing structures of NO2. What about N2O5? Take a look. NO. This is the structure, the classic structure of N2O5. Double single resonance is here, double single resonance is here. So, second possibility, NON. This double and this single, this stays as it is. No change. In this case, we make a change. Second structure. Third structure, when we change this and don't change it. So you have NON. Like this. And then there is a fourth and the last possibility when we change this as well as this. So NON, OO, O, and O. 1, 2, 3, 4. 4 contributing structures of N2O5, amongst which, if you look at the bond order, you would find some very interesting terms. There is resonance here, and there is resonance here. And bond order of these NO bonds is 1.5 each, and bridging NO bonds have simply bond order 1. So there are 2 types of bonds with N and oxygen. Single bonds with bridging, and 1.5 is the bond order with the terminal oxygen atoms. HNH bond angle is higher than HPH, HASH and HSBH angles. Why? Well, if you look at hydrides of group 15, you find there is something very interesting. Ammonia or NH3 has sp3 hybridized nitrogen atom. How do we know this? We know this because the bond angle, the NH bond angle in ammonia is around 107 degrees, which is close to 109 degrees 28 minutes, which is the classical tetrahedral bond angle. On the other hand, if you look at phosphine, arsine or stibine, you find that phosphorus, arsenic and antimony are unhybridized. How do we know this? We know this because these bond angles, HPH, this is 94 degrees only. This is 93 degrees. This is around 92 degrees. So H, ASH, H, SBH. These are approximate bond angles which are close to 90 degrees. If they're close to 90 degrees, it means that unhybridized p orbitals have been used in the bond formation or bond overlap. So, if you just see, in case of nitrogen, what happens is you have 2s and 2p. And they mix and you get sp3. And these sp3 hybrid orbitals of nitrogen, they overlap with s orbitals of hydrogen to form ammonia. In this case, since bond angles are observed to be close to 90 degrees, it means that there is no such mixing of orbitals in case of phosphine, arsine and stibine. Ns orbitals, Ns2 stays apart, and Np3, these are the orbitals which are used in bonding. I'll just draw them and show you. You find that you have 1, 2 and I'll just draw x-axis, y-axis and say z-axis like this. See? And these are mutually at right angles with each other. And that's why, these are the 3 p orbitals of hydrogen atom, phosphorus atom or arsenic or antimony. And as they form bonds with hydrogen atoms, you get these close to 90 degrees bond angles. So since the central atom does not undergo hybridization in phosphorus, arsenic or antimony, you have bond angles closer to 90 degrees which are much lesser than 107 degree bond angle of ammonia. Why? Because in ammonia, nitrogen undergoes sp3 hybridization. There is mixing and the ideal bond angle becomes close to the tetrahedral bond angle of 109 degrees 28 minutes. That, my dears, is the reason. Why does R3p double bond O exist but R3H double bond O does not? Well, that's very simple. Let me draw the structures. If you have R3p double bond O, just count the number of bonds formed by phosphorus. 1, 2, 3, 4, 5. Phosphorus has 10 valence electrons. This is a case of expanded octet. Can we write down the electronic configuration? Yes. Phosphorus in ground state was 3s2, 3p3. And in excited state, it changes to this. Watch this. And I hope you can see that in this case, this is sp3 hybridization. As you can see with the 4 sigma bonds. And there is 1 pi bond. And this pi bond is being formed by the electron which had been excited to d subshell. Now, d subshell is something which is available with phosphorus because principal quantum number is 3. You have 3s, 3p and 3d. Nitrogen does not possess 2d orbitals. Only 2s and 2p exist. Since nitrogen cannot expand the octet, it cannot form a similar geometry. And that is the reason why N double bond O R3 is not possible, because of non-availability of 2d orbitals in nitrogen. Explain why ammonia is basic but bismuthine is only feebly basic. There are 2 very beautiful reasons. First of all, please appreciate what is basic strength. The tendency to donate the lone pair of electrons. The tendency to donate the lone pair of electrons to another party which is electron deficient, forming a covalent bond or a coordinate covalent bond, that is called basic strength. Ammonia is sp3 hybridized. So the lone pair also lies in sp3 hybrid orbital. Lone pair in sp3 hybrid orbital. Fine, good enough. If you compare bismuthine, And please note, this bond angle is how much? Around 107 degrees. In bismuthine, there is a difference. BIHHH. This bond angle is around 91.5 degrees, which is close to 90 degrees. That means bismuth hydrogen bond is formed by unhybridized P and S orbital. Bismuth has unhybridized P orbital and hydrogen has, anyway, hydrogen cannot have any hybridization anyways, it has just S orbital. Okay, what does that mean? Now look at electronic configuration of bismuth, 6s2, 6p3. Now these orbitals are used, and this is inert. So the lone pair lies in pure S orbital. S is for strength. If a lone pair lies in S orbital, it is strongly attracted by the nucleus and it is difficult to donate. If the lone pair lies in sp3, now this has 100% S character. And this has only 25% S character. Greater the percentage of S character, number one, more strongly is the orbital attracted or the electron attracted by nucleus, and it is difficult to donate it. If it is difficult to donate, the basic strength decreases. Also, S orbital is spherical. It is on all the sides. A spherical electron pair is more difficult to donate on one side. In sp3 hybridization, it is already on one side, so it just gets donated much more easily. Also, there is a third reason. This is second shell and this is sixth shell. Sixth is a big shell. Volume of 6s electron is very high, and greater the volume on which the electron has been spread, it is more stable and less reactive. Because of all these three reasons, you find that donating the lone pair for bismuth becomes much more difficult, and the basic strength becomes so less that it is practically non-basic completely. Nitrogen exists as a diatomic molecule and phosphorus as P4Y. Nitrogen is a small atom, and nitrogen is capable of forming stable p-pi overlaps. If you move down the group, phosphorus becomes bigger atom. Bigger atom. Now, as atomic radius increases, the strength of bonds decreases, yes, but there is also a different trend. Sigma bonds become longer, they become poor, yes. Pi bonds also become longer, yes, and they become much more poor. Okay, what does that mean? The strength of sideways overlap is very, very, very poor if you move down the group. So, you find that phosphorus is incapable of forming stable pi bonds with another phosphorus atom. If the other atom is small, like nitrogen or oxygen, there is still a chance. But if the other atom is also phosphorus, now N triple bond N is very stable. P triple bond P is not stable at all. So because N triple bond N is very stable, it can be formed. Because P triple bond P is not very stable, it is not formed. On the other hand, if you have 4 phosphorus atoms like this, and if these, if you find, and if these can be joined like this, each phosphorus has formed 3 bonds. The valency is satisfied, octet is complete, and in addition, there is no need for forming any pi bond. This is a more stable arrangement in case of phosphorus because sigma bonds are significantly better than pi bonds. And that is why, my dears, phosphorus loves to remain as P4 because it does not need to form pi bonds here, and nitrogen loves to remain in N2 because it can form very stable pi bonds, and this is the best way in which it is forming pi bonds. Write the main differences between the properties of white phosphorus and red phosphorus. Now, white and red phosphorus actually are two allotropes of phosphorus. What is the meaning of allotrope? If the same substance, the same chemical substance can exist in more than such structures that they have different chemical properties. Please note, chemical formula is the same, but if they have different physical and chemical properties, then they are said to be allotropes. Okay, like you have white and red phosphorus. White is sometimes also called yellow phosphorus. And do you know, there is a very fundamental difference in their structures. What is the difference? The difference is like this. White phosphorus exists as P4 units like this. This is the structure of white phosphorus. So white phosphorus has discrete molecules containing P4 units. And the most fundamental difference is when you're talking about red phosphorus is polymeric. It has no small molecules. It has actually, the structure is actually inspired by white phosphorus only. I'll just tell you how it is like. Now, instead of making one more bond here, you just make it outside like this. So these tetrahedral units, now one of this bond, this bond opens up and they form cross linkages like this. So it becomes relatively more stable. This is less stable and more reactive. This is more stable and less reactive. Two fundamental points. If you want to point out more differences, first is color, white and dark red, yes. Also, white phosphorus is soft, waxy solid. Red phosphorus is relatively harder. Hard doesn't mean it is as good as iron, no. It is harder than white phosphorus, it is more crystalline, fine. Both of them are insoluble in water because they are not polar. But because white phosphorus has small different molecules, it can dissolve in carbon disulfide, which is also a non-polar solvent. Red phosphorus is a polymer, and polymers don't dissolve in anything, so it is insoluble in carbon disulfide also. Because it is less stable, it is highly reactive. It catches fire in air at even 35 degrees Celsius. Now we are in Kota, Rajasthan, where in summers the room temperature itself is around 45-46 degrees Celsius. So white phosphorus will simply burst in flames in a place like Rajasthan. Red phosphorus, it takes around 200 degrees Celsius to burn. So I mean, you have to heat it to burn. It won't ignite on its own on Earth's surface very easily. White phosphorus is highly poisonous. It is used as a rat poison, which means that if you feed it to rats, rats die. It doesn't mean that humans can't die, just that they'll have a very bad time, and if they eat more, they also will die. Red phosphorus is innocent and non-poisonous. Nothing much happens out of it. There could be more differences, but for exam point of view, these are sufficient. You should write at least 4. If you write 4, and I have given you 1, 2, 3, 4, 5, and 2, 6, 7 points, any 4 points are good enough in this. Why does nitrogen show catenation properties less than phosphorus? What is catenation? The property of direct bonding between atoms of same element. That means if nitrogen can form bonds like N, it can go on forming bonds like this. If this is possible, I'm not saying this happens. If this is possible, we would say nitrogen catenates. If phosphorus can form bonds P like this, we can say phosphorus catenates. Which has greater tendency? Phosphorus actually has a greater tendency to catenate as compared to nitrogen. Phosphorus can form red phosphorus, which has P, long chains of phosphorus atoms. Nitrogen cannot form this. As a matter of fact, the longest it can go is azide ion. N3 minus, that also has a minus charge. And this also is explosive, it is unstable. Nitrogen hates any kind of catenation. Why? That is the question. Why? It shows catenation properties lesser. See, the length of NN bond is smaller than the length of PP bond. Yes. So nitrogen is supposed, because bond length is less, we might expect that the bond strength should be more. No, that is not the case. Why? The tragedy in the case of nitrogen is because of the lone pair of electrons. Each nitrogen atom actually harbors a lone pair of electrons. Yes. And lone pair. Now, if nitrogens are forming a bond, there is a repulsion between these lone pairs. And because of this repulsion, the strength of NN single bond becomes very poor. And that is why hydrazine, what is hydrazine? It contains NN single bond and HH like this. Hydrazine is very unstable and very reactive because NN bond is very, very weak. Okay. What about phosphorus? In case of phosphorus, atoms are bigger. So bond length of phosphorus is a little more than nitrogen. And because of longer bond length, now lone pairs are far apart. Repulsion is there, but repulsion of lone pairs is not as much as in the case of nitrogen. In case of nitrogen, the repulsion between these lone pairs weakened the NN single bond much more. In this case, lone pair repulsion is there, but it does not weaken the PP single bond as much. And that is why PP single bond is still not as bad as NN single bond. And because it is a stronger bond as compared to NN. Phosphorus, because the bonding is stronger, it can catenate. And nitrogen, because bonding is poor, it does not catenate. That, my dears, is the reason. Give the disproportionation reaction of phosphorus acid. If H3PO3 is heated, you find it disproportionates to H3PO4 and phosphine. If you heat it above 300 degrees Celsius, around 320, 350 degrees Celsius, you find it very easily disproportionates to give you H3PO4 and phosphine. Like this. This is the reaction. Can PCl5 act as an oxidizing as well as reducing agent? Justify. Well, oxidizing agent is something which oxidizes others and gets itself reduced. Is that possible for PCl5? Well, if you just see PCl5, it is not impossible that PCl5 actually goes around oxidizing something else. Why? Because phosphorus is in +5 state, and although phosphorus is reasonably stable at room temperature in +5 state, if you heat PCl5 strong enough, if you heat it in chemical equilibrium also, you might have seen it decomposes to PCl3 and Cl2 in vapor phase around 500 degrees Celsius. And the chlorine it releases can oxidize others very easily. So in that sense, it can function as an oxidizing agent because it is releasing also a very popular oxidizing agent, chlorine. A very good example can be seen with many other substances, like if you heat PCl5 with sulfur, you get PCl3 plus S2Cl2 like this. You get reactions like this. Now, the PCl5 can act as an oxidizing agent, yes. Can it act as a reducing agent? If PCl5 has to act as a reducing agent, then PCl5 has to reduce others, and in that process, PCl5 must get itself oxidized. PCl5 must get itself oxidized because all reducing agents reduce others and get themselves oxidized. Now, PCl5 contains phosphorus in +5 oxidation state. +5 is the highest possible oxidation state of phosphorus. Phosphorus cannot go beyond +5. And since phosphorus itself cannot undergo oxidation, its PCl5 cannot get oxidized, and that is why it cannot function as a reducing agent as such. So, PCl5 can function as an oxidizing agent, yes, and that also is not very pleasant or easy, but it definitely does not function as a reducing agent. Justify the placement of oxygen sulfur, selenium, tellurium and polonium in the same group of periodic table in terms of electronic configuration, oxidation state and hydride formation? This seems to be a very interesting question. They're trying to ask, why are they in the same family? That means they should show the same trend in properties. There should be some generic commonality. And this is what we are supposed to bring out in terms of these three things. So first, let us take a look at electronic configurations. Let me remind you, oxygen, sulfur, selenium, tellurium and polonium, all these elements together are called chalcogens. Fine. Now, they have 6 valence electrons. That means the general electronic configuration is NS2, NP4. So, oxygen is 2s2, 2p4. Sulfur is 3s2, 3p4. Likewise, polonium would be 6s2, 6p4. Okay. So, this N varies from 2 to 6 and you have oxygen, sulfur, selenium, tellurium and polonium. Oxygen and sulfur are non-metals. Selenium and tellurium are metalloids and polonium is a metal. Is that significant? Very significant. They have a number of different oxidation states, -2 being the lowest. Oxygen loves to stay in -2. Sulfur, selenium and tellurium can visit -2. They can remain in -2. Yes, polonium is a metal and polonium hardly shows -2. That minus is here, 2 is here. Don't get confused. So polonium, actually for all practical purposes, polonium would not exhibit a -2 state at all. Right? Now, oxygen, does it show positive states? Oxygen can be a maximum of +2 and that also only with fluorine. The oxygen forms OF2 or O2F2 in which oxygen can show +1 and +2, but that is rare. Otherwise, oxygen is always negative. Sulfur, selenium, tellurium and polonium, they very well can go to a higher state of +6. So yes, they can go to +6 and they can also exhibit +4 and rarely, like sulfur, can also give you +1 and +2 states, but that is not the trend for selenium and tellurium, so let's skip that. So they can show +6, +4 and -2. A rarer state of +2 but not very popular. And again, these higher states of +4 and +6 are not shown by oxygen. This, my dears, is a common trend down the group when it comes to oxidation states of chalcogens. Hydride formation also is very interesting. They always have H2E, like H2O, H2S, H2SE, H2TE. H2PO is very unstable. Polonium is a metal. The polonium does not form hydrides. So we have oxygen, sulfur, the nonmetals, selenium, tellurium, the metalloids. All of them can form this H2E. That means a hydride which contains 2 hydrogen. If you move down the group, you find that hydrides become less stable. So yes, you find bond length increases for H element bond. Bond strength decreases, reducing power increases, HEH bond angle also decreases and basic strength also decreases on moving down the group for H2E in general. These are the properties.